Welcome to another video on Circuits Decoded. The topic for today is strong arm latch comparator. It is one of the most widely used comparators in mixed signal designs. Dynamic comparators are usually clock driven and do not consume any static power. It only consumes current at the rising or falling edge of the driving clock. We'll try to understand its detailed operation, analyze its noise, and come up with some design considerations. So this is the whole circuit. I have marked each group of transistors with a specific function with a particular color. The red group is the reset switches, which reset the drain nodes to VDD. The yellow ones are the input devices, which convert the input voltage to current. The bottom green transistor is the enable switch, which enables the circuits when the clock is high. And finally, the white transistors realize the latch function of the comparator. Now let's study the operation of the comparator in different phases of the clock. The first phase is known as the reset phase. It starts at the falling edge of the clock and lasts till the clock is low. In the circuit figure, the non-highlighted devices are off and the solid highlighted ones are on. In this phase, since the clock is low, we can see that only the PMOS reset switches are on. The reset switches pull the Vx, Vy, Vp and Vq nodes to VDD, as shown in the timing diagram on the right. The capacitors Cx, Cy, Cp and Cq represent the parasitic capacitances on the respective nodes. The second phase is the amplification phase, which begins as soon as the clock toggles to VDD. As the clock is high, the reset switches are off and the bottom switch enables the comparator, which means it allows the capacitors to discharge to ground. The input differential pair converts the differential input voltage delta V to differential current, which in turn creates a differential voltage between Vp and Vq nodes, as shown here. On top of the differential current, there is a common mode current ICM, which discharges the capacitors Cp and Cq. Since the latch NMOS transistors are off in this phase, the Vx and Vy nodes remain at VDD. The time duration of this phase is denoted by Tph2, which lasts till the common mode voltage of Vp and Vq has dropped by the threshold voltage of the NMOS transistors, VTHN, as shown here. At this point, the NMOS transistors begin to conduct. Now, if we work out the capacitor-CV relationship, an expression for Tph2 can be derived as shown here. Now, as for the differential voltage Vp minus Vq, it can be treated as small signal. And so, assuming the input transistors in saturation and its transconductance as Gm, the voltage difference between Vp and Vq can be written as shown here. Now, by dividing both sides by delta V, we arrive at the gain expression in this amplification phase, as denoted by AV. In the next phase, the latch, or more specifically the NMOS transistors M3 and M4, begin to conduct. As Cx and Cy begin to discharge, in the positive half of the circuit, we can see that the input current is split between Cp and Cy. And the same thing happens between Cq and Cx capacitors in the negative half of the circuit. The node voltages are no longer linear, as shown here. The expression for these node voltages can be found by solving a first-order differential equation. I'll provide the reference where you can find the derivation later. But the time constant of the node voltages Vx and Vy is given by tau ph3 as shown here. We can see that the time constant is Cx over Gm3 divided by 1 minus Cx over Cp. The term 1 minus Cx over Cp increases the time constant of the nodes, so the discharge rate is slow in this phase. Intuitively, we can see that the capacitors Cp and Cq cause degeneration in the small signal model, and the effective Gm of the NMOS transistors is reduced. This lowers the time constant tau ph3. Although the rate is not high, the node voltages Vx and Vy don't take long to discharge by an amount equal to VTHP, which is the threshold voltage of the PMOS transistors. At this point, the PMOS transistors begin to conduct, and it marks the end of this phase. The final phase is the regeneration phase, which is when the latch is fully on. Now, by virtue of positive feedback, one of the nodes Vx or Vy is pulled to VDD and the other is pulled to ground, as shown here. In our example, Vy is pulled to VDD and Vx to ground. On the other hand, both Vp and Vq nodes are discharged to ground. After Vx and Vy reach valid logic levels, the decision phase is over and another latch or a flip-flop stores the output voltages before these nodes are reset again to VDD and the cycle repeats. An interesting thing to note here is that once Vx and Vy are settled, the latch disconnects the direct path between the supply voltage and ground. In this example, we can see that since Vy is VDD, the upper left PMOS is off, and since Vx is ground, the lower right NMOS is also off. So the direct path between the VDD and ground gets cut off. The speed and power consumption of a strong arm latch are well defined. The speed is given by the parameter tcomp, which is shown in this equation. It is essentially the sum of the times of the three active phases: amplification, phase 3, and the regeneration phase. The power consumption pcomp is given by this equation and is in the forms FCVDD square. Interestingly, it does not depend on ICM or the common mode current. The factor 2 before Cp is because both Cp and Cq are discharged to ground, and the factor before Cx is 1 because only one of the capacitors, Cx and Cy, is discharged to ground. Now let's consider the offset due to the capacitor mismatch. Since the first stage provides amplification, the input revert offset of the second stage latch can be made very small and therefore ignored in the following analysis. If we work out the current voltage relationships with unequal capacitors, we can find the error voltage delta VPQ as shown in this expression. Here, TPH2 is given by the average of Cp and Cq times the threshold voltage over ICM. Substituting TPH2 in this expression, we can further simplify the offset voltage as shown here. Here, delta C is the total mismatch between the two capacitors. With this, we can write the standard deviation of the offset voltage as shown here. Now, if we consider the mismatch between the two input transistors, we can write the input referred offset variance as shown here. In this expression, sigma square M12 is the variance of the threshold voltage mismatch of the two transistors. And the second term refers to the input referred offset component given by the capacitor mismatch. Now, like the offset voltage, the noise is also mostly due to the first stage transistors and the sampling noise at the Cp and Cq capacitors. The variance of the MOSFET current noise is due to the noise current integrating on the capacitors and is given by this equation. Now I'll not go into the derivation of this as you can find it in the reference, but note that the variance increases with the integration time t. In the time duration tph2, the variance can be simplified as shown here. Here, VOV is the overdrive voltage of the NMOS transistor, which is given by VGS minus VTH, and GM is given by 2 ICM over VOV. Now adding the KTC noise due to the sampling operation, the noise variance on Vp minus Vq is given by this expression. This expression, when divided by the gain of the amplification phase, gives the net input referred noise variance as shown here. Now it's time to get some design considerations based on the power, speed, and noise expressions as shown here. The power consumption of the circuit is proportional to the sum of the node capacitors. The speed is proportional to ICM, and the input referred noise variance is proportional to the overdrive voltage VOV and inversely proportional to the parasitic capacitor Cp. Now a design question is, how does increasing or decreasing the input common mode voltage impacts the noise, speed, and power consumption of the comparator? So firstly, increasing the common mode voltage would increase the V over drive voltage, which in turn increase the noise power. Also, increasing the common mode voltage would increase ICM and therefore would improve the speed. As for the power consumption, it does not depend on the common mode voltage and therefore would remain fixed. We can utilize these three expressions to optimize the comparator for speed, power, and noise. So that's it for this video. If you like my work, please subscribe and I will see you in the next one.